Hello and welcome to the next part of Framsticks tutorial. Today I will speak about something very useful, which is modifying standard experiment definition so that you gather additional information about behaviors of creatures. And then you can do a lot. You can really do everything you want with this information. But first, you need to somehow gather information about what happens during lifespans of creatures, and then you can evaluate it. Then you can add some penalties to fitness function depending on what the creature was doing, how it was interacting with other creatures, with the environment, and so on and so on. Let's look at our tutorial, customizing standard experiment definition. I mentioned many times that this experiment definition is very powerful. It's like a versatile tool to evolutionarily optimize creatures. Now we will just learn how to propagate some information about the behavior to the fitness function of the genotype. And we will have this important distinction between creatures, which are alive, simulated, and genotypes, which are dead, but at the same time, genotypes correspond to creatures. So everything that happens to the creature, and for example, we like it or not, we have to propagate this information to the genotype because the genotype exists in the genetic space where this search and optimization takes place. If you want to evaluate some kind of a complex lifetime behavior, really you can do a lot of cool things with this that cannot be expressed as an aggregation of pre-computed performance indicators like velocity, lifespan, vertical position, and so on. Remember our previous part of the tutorial when I explained how to customize fitness function? We only used, in this previous part of the tutorial, we only used existing performance criteria. And now, this part of the tutorial is about defining your own completely creative and complex fitness criterion. Anything that you can imagine that depends on lifetime behavior of creatures. You can use creatures data dictionary to store any information you need. So both the creature object and the genotype object have data dictionary. And as usual with dictionaries, you can store anything you want. Nested dictionaries, vectors of dictionaries, dictionaries of vectors, whatever you need. You can modify values in the data dictionary in each simulation step, depending on where the creature is, what it does, and how it behaves. So it is up to you to store anything you need. If you want such evaluation to be used as fitness, you have to propagate it from creature to genotype. And this is a tricky part, because at some point the creature will die and it will no longer exist. So you have to move just before the creature dies, or when it is about to die, to be removed from the simulation. You have to propagate everything you gathered during lifetime to the genotype, to the corresponding genotype, and then probably aggregate it somehow so that it is propagated to fitness. And fitness in one criterion optimization is only one value. Of course, you can use multiple criteria optimization in Framsticks as well, like NSGA2 or some other algorithm, but for now, let's keep it simple, or at least this component, let's keep it simple. Find the following line in standard experiment definition. Want to copy customized values, and assign the fitness component that you computed and stored in creatures data to some key in the data dictionary of the genotype, G. Then, in the fitness formula, which is defined for genotypes, you can use this key in the data dictionary of the genotype. So first you propagate from creatures data dictionary to genotype data dictionary, and then you propagate from genotype data dictionary to fitness. The custom fields dictionary of a genotype and a creature can be displayed in Framsticks graphical user interface, which is helpful for debugging. Certainly we will use this feature. Example: copy standard experiment definition to standard my experiment definition. So contrary to our previous part of the tutorial, now we will be properly not modifying this existing official distribution version of standard experiment definition. We will create our copy and then we can do whatever we want. So go to data scripts and do this copy and rename. At the end of the function onBorn, add the following two lines. Okay, I will copy those two lines. We have function onBorn. It does something, and at the end I insert those two lines. And what those lines do? We have a newborn creature. It didn't live so far, it was just located, placed in the simulation, and we immediately create in this data dictionary two keys and two values, max height field and height history. We will not use this height history in any way. It will just demonstrate, and I introduce this to demonstrate to you that you can indeed store some historical data from the lifespan of the creature. So we will be recording height of the creature in different moments in time. And by the way, we see here this alternative notation of dictionaries. So the proper, or maybe the standard way, would be something like this. So this is maybe now more apparent that we are indeed creating in the dictionary, creating a new key, and at the same time we could write it like this. So it's completely equivalent. This is just like a shorter notation to access keys in dictionaries. And from this point on, we have to remember that we created those two keys and these are keys for us. We have full control over those keys. Save the file, I did. Run Framsticks graphical user interface and activate this experiment definition. How to activate experiment definition? You open all parameters in Framsticks and from this list you choose your experiment definition. You can, for example, press apply. And the only difference of this experiment definition compared to the default experiment definition is that every time a new creature is born, it will have those two additional fields in the dictionary initialized. Add one X genotype and simulate it. Double-click the living creature in the populations list and see custom fields dictionary in the current performance category. Simulate the simplest genotype, revive it, double-click, and current performance, custom fields dictionary. Indeed, we have those two keys in this custom fields dictionary initialized exactly as we wanted. This will happen when every creature is born. I think it will also work for food, so I will just add a food item and see, yes. So food items, they just exist in a different population of those two populations, so food items also have those two keys created in the dictionary. Back to editing. At the end of the function onStep, add the following lines. Okay, I will add them and then we will try to analyze them. Function onStep, where it ends. Here it ends. This is the location where we recently added jiggling. Remember? This dangerous experiment. Okay, I pasted this. This function, the onStep function, is called once in every simulation step. And in this piece of code we added, we iterate through all creatures in the first population. So this will not work for those food items because they are in population number 2 or 0 based population number 1. And now we only take population 0 or 1 depending on how you number them. So for all creatures in this population which are in this performance measurement activated period, remember this waiting for stabilization period? If a creature is in this waiting for stabilization period, this logic will not be effective because this condition will be false. So only when the creature is actually alive and its neural network is active, it's past this stabilization period, or even this stabilization period was, for example, deactivated by you. So every creature immediately after putting into the simulation is active, then this logic will be effective. And what we do in this logic, calculate height as the lower bound of this bounding box and then deduct bounding box ground offset. So we simply see how much above the ground is the bounding box of the creature. Then we increase this max height key in the dictionary of the creature, in this private dictionary of each creature. We are just increasing it when this distance between the ground and the lower part or lower bound of the bounding box increased. And finally, every 10 simulation steps, again referring to this private simulation steps counter of each creature, because remember, for example, when you revive 100 creatures, each of them may be revived after stabilization in a different moment in time. So we shouldn't use global step counter or this step number counter in the simulator. Better use private counters of steps in lifespan for each creature. So every 10 simulation steps, record height in history from every 10th time step, okay? And remember, since this height history was initialized as an empty vector, we will be simply appending current height to this vector. Save the file. In graphical user interface, go to parameters, click reload experiment definition, okay? We should not forget this. Reload experiment definition, and close the parameters window. Add one X genotype, simulated a few hundred steps until its energy starts to decrease. So I create one genotype, I simulate it, and I look carefully here so that it doesn't die. I will just run the simulation and wait until this becomes on. Okay, 900, 800, 700. I will stop now. Double click the living creatures in the populations list and see custom fields dictionary in current performance. So this is what we did earlier. We just expect our dictionary to have some values. Okay, we have some height history, and at the end of this field we have also max height initialized to some value. Of course, you could copy the entire contents of this field and paste it in a text editor so that you see this entire contents, because remember, we are adding to this dictionary and to this vector every 10 simulation steps. So we have gathered a lot of data so far. The last thing we need to do is to handle the propagation of information from a dying creature to its genotype. So find the text want to copy customized values from creature's data and add there the following lines of code. There is a long comment here and it is important, so let's read it. Want to copy customized values from creature data fields to genotype data fields. This is exactly what we want now. Do it here or in a specialized simulator user script function C, let's ignore it for now. G data my field becomes creature data my field. So this is exactly what we wanted. A creature is about to die. We need to save those stored data in the corresponding genotype. Want to take instances into account? Do it here. What's about instances? Remember, genotypes may have many copies. They are called instances. So a single genotype may have many copies. This is because you may take one genotype and simulate it many times, like for example 10 times, and 10 creatures, 10 clones of this genotype will die, and then you can either have 10 copies, separate copies of individual, the same genotype in this gene pool, or you can somehow aggregate this information and average those performance values instead of having 10 or more separate copies. So, if you wanted to aggregate this information from many clones of the genotype into a single genotype, you can use this formula G data my field instead of this simple assignment above is this data my field value multiplied by the number of instances, the current number of instances, plus this new value and divided by the number of instances increased by 1, because this is like adding one additional measurement to existing measurements, and you have to calculate this weighted average appropriately. For example, you had 10 genotypes already, and now you get 11th copy, 11th clone. So you multiply existing performance value times 10, you add your new measurements, and you divide it by 11. Okay, this is the logic. So if you wanted to implement it properly, you should actually use such formulas, because then your solution is more general. It will work for this single instance of each genotype, but it will also work when those instances will become higher and each genotype will get more copies, more instances than one. Okay? So I add here this piece of code. And the first line is only a diagnostic message that displays these historical height values. We do not do anything with this information, so I added this line only to indicate that when the creature dies, we have access to this kind of data. And obviously, it's up to you, up to the person who implements this logic, to somehow aggregate or evaluate this information that was gathered during the lifespan of the creature. And remember, height is just an example. You could, for example, store coordinates or energy level or whatever you consider important for your goal during the lifespan. And this is the location where you propagate this information from creature to genotype. And you do not necessarily want to copy everything that was stored during the lifespan of the creature. This is where you should have some logic of aggregating, evaluating this historical information, and then you will turn it into fitness. Okay, this is the entire goal. Then we update this average based on instances. First we check whether this genotype has initialized this key in its dictionary, because if not, we do not need and we are even unable to calculate any value of weighted average. So if there is no such key, we simply create this key by using the raw value from the creature. But otherwise, if this genotype already has this key in its data dictionary, then we can use this formula I discussed earlier, to calculate this weighted average, to add new measurement to existing measurements. Save the file, go to parameters, reload experiment definition, close the parameters window, add a new genotype, open messages, run the simulation until the creature dies, and inspect this dictionary of the genotype. We didn't see anything in the genotype so far. We reload the experiment definition, we create a new genotype, we run the simulation, wait some time, some new genotypes are created, stop the simulation. First of all, we see in our messages window those messages which are printed every time some creature dies. So this is where we lose this historical information, because I do not do anything except from displaying it. But at the same time, we should be able to see in our genotypes, in the performance category, custom fields dictionary. Okay, so this is where this information was propagated from a creature to its genotype, and if we had the number of instances higher than 1, then this would be properly calculated and the average, the weighted average, would be updated. And there is only one step left to propagate this information from this data dictionary in the genotype to its fitness value. And it's very pleasant and simple, because this is the last step. Set the fitness formula of the genotype's gene pool to, this is where we use this prepared value from the private dictionary of the genotype. So we can simply write return this data max height and a semicolon. Genotype, replace this definition with this definition, and immediately after I click OK, I should see fitness updated. And indeed, those fitness values should correspond to this private key. So for example, we have this value here, and indeed it got propagated to the fitness value. Now evolution will use this information that you carefully calculated based on what was happening during the lifespan of the creature. In simulation parameters world, set type to height field and map to 4x4 height matrix. So let's copy this height matrix. Set the type of the world to height field. Copy this matrix here. It's a 4x4 matrix, so it could be formatted in a more friendly way, just by splitting it into lines. Press OK, and now you can see that this world is shaped in a slightly different way. Okay, now you can perform evolutionary optimization according to fitness, which is, you know what it is, and you know how this height is calculated. So this was just an example, but a very, very useful example. Now you can get creative and you can guide evolution in any direction you want based on what creatures do during their lifespan. Later, in the following part of the tutorial, I will show you how to use Framsticks interfacing with some external environment. For example, launching Framsticks from Python and performing evolution in Python, or maybe using client-server architecture. But everything I said so far, and in particular this part of the tutorial, is still very useful, because no matter what other environment will be interfacing Framsticks, you will always need to simulate creatures and control them in some way, and probably gather some statistics. So this was really important from the point of view of performing multiple experiments, multiple ideas you may have. So see you in the next part of the tutorial.